Cells and batteries. Welcome back to part 3 of static and current electricity, magnetism and transformers. Yes, I can't remember, I have it written down, don't worry. And now we're moving on into cells and batteries. The electromotive force required to drive a current can be produced by chemical reactions between acids and metals. Each cell has two terminals or electrodes. One is positive and the other one is negative. You could just look at your battery and see that. You see it all the time. I'm going to do a demo right now. It has it there. So the positive end is a nipple, and then you have the negative end up here. Now, cells are restricted in the size of the current they can provide by the internal resistances, which are due to their physical and chemical composition. A typical cell is a primary cell, and here you have the seal and insulator on the top. You have a carbon rod, that's the one that goes from the nipple right down to the bottom. The zinc casing, the case is made of zinc, which is negative. Aqueous ammonium chloride just on the inside of the casing, then powdered carbon manganese dioxide, which makes up the bulk of it in here, that's surrounding the rod. Then you have an insulator at the bottom. Car batteries are secondary cells, and many of you, if you have a car, you would have seen these. That are protective casing, positive terminal, negative terminal, and usually they would have the signs, plus sign for positive, the negative sign for negative. You have the cell dividers, positive electrode, lead dioxide. The negative electrode is made up of lead, and the liquid inside is dilute sulfuric acid. So here are the comparisons between the two. I tabulated them because most books have them written out, but I think it's best if they're tabulated and you can compare. So we have primary cells. The most common type of primary cell is a zinc carbon cell, and the most common type of secondary cell is a lead acid cell. The chemical reaction which produces the EMF cannot be reversed in a primary cell. However, it can be reversed in a secondary cell. In primary cells, they cannot be recharged or reused, but in secondary cells, they can be recharged and reused. An EMF of 1.5 volt is produced when the negative zinc case and positive carbon rod and aluminum chloride paste reacts. That's in primary cells. An EMF of 2 volts is produced when a reaction occurs between the negative lead plates and positive lead oxide plates and dilute sulfuric acid. They have high internal resistance. In the primary cells, they have high internal resistance, therefore it cannot produce a very large current, a maximum being 1 amp. And the secondary cells, they have very low resistance and can provide very large currents. And primary cells, once used, the chemical reactions continue to take place even when they're not in use. So once you put them inside of the appliance and you stop using that appliance, after a while the battery gonna die anyway, because it's gonna use up all the chemicals that it is made up of. So over time they become useless. In secondary cells, chemical reactions only take place when in use, so they last longer. Resistance. Resistance is a measure of the opposition provided to an electrical current. It is the ratio of the PD across a conductor to the current through it. When electrons flow through a conductor, they are obstructed by vibrating atoms in their paths. These atoms therefore decrease the rate of flow of the electrons and hence the current. Electrical meters are used to measure both current and potential difference, but the meters must be placed carefully in order to operate correctly. So here is the way you place them. The voltmeter is placed across the either the appliance, or if you want to check the voltage across the cell, they place it across that, right? The ammeter is placed in series. So voltmeters are placed in parallel, Well, ammeters are placed in series. All components have a resistance to a current. Metal wires have low resistance, while glass rods have a high resistance to current. So we're going to compare the two now. So we're comparing ammeters and voltmeters. So these are the two meters used in circuitry. Ammeters are used to measure the current at a point in a circuit, while voltmeters are used to measure the potential difference between 2 points in the circuit. Ammeters, they are placed in series with the other components. Placing the meter in this position reduces the current. Voltmeters are placed in parallel with the components, that is, measuring the potential difference across. Ammeters, they have very low resistance to allow the easy passage of current, and voltmeters, they have very high resistance so that almost no current will pass through them. Okay? When you're calculating resistance, this is the equation we use. You divide the voltage by current, and the unit for resistance is the ohm. I'll harshly people call it, but the real name will be ohm. A simple metal wire will have a constant resistance as long as its physical properties and conditions do not change. The relationship was discovered by George Ohm and is called Ohm's law. The current through a conductor is directly proportional to the potential difference across it. Okay? So the constant of proportionality is resistance. Materials which obey Ohm's law have constant resistance. They are called ohmic conductors. If a material is an ohmic conductor, a graph of I against V or V against I is a straight line to the origin. In some materials, resistance is not constant. This behavior is classified as non-ohmic. Ohmic conductors may be metal wires. They conduct best when they are short and fat. So the fatter they are, the less resistance to the electrons passing through, more space for a lot of electrons to pass through. And these are called ohmic conductors, and you will get a graph, a straight line graph like this passing through the origin called 0. See the origin right here? This is the origin. Filament lamps conduct best when current passing through them is low. So they behave like ohmic conductors until a certain point. You see the straight line here? They behave like ohmic conductors. If the current is increased, the filament will get very hot, increasing resistance. So remember, when heat is applied to a wire, it doesn't behave like how it should. And the filament lamp behaves as ohmic conductors once the wire does not get too hot. So after a while, it starts to act like this once the filament gets hot. So it's actually an ohmic conductor once it's not hot. Not too hot. Ionic solutions or electrolytes have a higher resistance to current than metals. The more concentrated the electrolyte, the less resistance there is to current passing through it. Instead of electrons, the charge carriers are ions present in the electrolytic solution. So the electrolyte is exactly like, remember the don't panic one? So that is the setup. So this one is also an ohmic conductor. So we have 3 ohmic conductors. You have metals, you have filament lamp, and you have ionic solutions or electrolytes. So basically salty solutions. A semiconductor diode is not an ohmic conductor. When a negative voltage is applied to it, the diode experiences a very high resistance. So very little current passes through it and is said to be in reverse bias. And that is how it's built to behave. In forward bias, the semiconductor diode has even higher resistance and almost no current passes through it. And this is the graph. The shape of the graph is the. So no, it's not straight line. You can't receive any straight line. No. Looks like a chair, bend up and a chair again. No. Now, how, where, and why are resistors used? Resistors are used within circuits to limit the amount of current entering components in order to protect them. Variable resistors may be used instead of normal resistors because their resistance can be altered by turning a dial or moving a sliding contact. Types of resistors. You have light dependent resistors. Description: you have low resistance to bright light and very high resistance to low light. Can be used to build light sensors and switch on lighting systems automatically when it gets dark. Then you have thermistors. Their resistance changes depending on temperature. Can be used to control heating or cooling systems. Calculating resistance in series and parallel circuits. So to calculate the resistance, the total resistance of resistors in a series circuits, all you have to do is add them. You add them together. To calculate the resistance in parallel circuits, you have to find the reciprocal of them. So basically, you're going to put 1 over it. So 1 over total parallel resistance equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so you just have to follow that, and when we get questions on it, we could work on it together. Alright, so here ends part 4 of our static and current electricity, magnetism and transformers. So see you around for part 5. Bye.